In this video, I want to just give a quick overview of Chapter 8. This might be a good thing to watch right before you dive into the detailed lectures to kind of give you like just an overview of what we're going to be doing. And really, this week, we're just continuing the work we did when we talked about covalent bonding. And so really, that is the theme for these few weeks. It's all about covalent bonding. And we're spending a lot of time on it, and it's still just an overview. This is such a rich topic. So within covalent bonding, I feel like there's really two pathways of thinking about and characterizing covalent bonds. And really, the kind of continuation of what we've been doing is first we talked about Lewis theory, and that gave us our Lewis dot structures that were these like two-dimensional kind of pictures of how atoms might be arranged together and sharing electrons. We improved Lewis theory with Vesper theory. And that gave us an understanding of what these molecules might look like in 3D. But it was based on a Lewis structure. So you start with a Lewis structure, and once you have that, you can then think about the geometry around any central atom that's bonded to more than one thing. And then that gives you this kind of like 3D idea of how these atoms are arranged in space to minimize the repulsions between electrons in atoms or lone pairs around a central atom. Or if you want it's such a terrible word, the electron group. I think that's what it was called. So we can now build on Vesper theory even more, because if we just take a look at how these geometries are arranged based on Lewis and Vesper theory, we can't really explain it. It doesn't make sense that everything is repelled based on where the electrons are in the orbitals. And so really it's trying to take this idea of Vesper and Vesper theory, Lewis theory, and like our ideas of the electronic structure of an atom, so electron configurations. And together, this doesn't make sense. We actually really need something else to explain it, because otherwise it would predict these really weird geometries with like 90-degree angles, and we just don't see that. So we need a better explanation. And that's where we get valence bond theory. Remember though, this electron configuration we were doing in our orbital diagrams, these were just kind of a bookkeeping method. For our electrons. It wasn't actually grounded in like what the electron's really doing. It's same with Lewis and Vesper theory. In fact, I would say all of this is really a way for us to impose a pattern on our set of observations of how covalent molecules arrange themselves to or how atoms arrange themselves into covalent molecules. But it's a pattern we impose so we can easily make predictions. And it works a lot of the time, but it doesn't do a good job of explaining what's actually happening in nature. And so this is a pattern for making predictions, and not really much more. But our brains sure do love patterns, and we really like to be able to predict things. So we're going to focus in this chapter in part on valence bond theory. But we're also going to introduce another one as well. And we won't go into it in too much detail. It is an introduction, so we're only going to handle the simplest of cases. And where it's going to come from is the quantum model of the atom. So all that Schrodinger wave equation stuff we did. And the electronic structure of electrons when they're so tiny that they can act as both a particle and a wave. So that actually leads us to molecular orbital theory, or MO theory. And this will be the other thing that we focus on in chapter 8. So chapter 8 is really giving us two different advanced bonding theories, and we have a foundation for both of these, but they are doing fundamentally different things. So I'm going to give a quick overview of each of these. And again, for more detailed information, please watch the lecture videos. So within valence bond theory, your problem solving strategy is going to kind of follow the same pattern. First, you're always going to need a Lewis structure to start with. Then you're going to need to interpret that Lewis structure using Vesper theory. Once you have an idea of how things will arrange in 3 dimensions, then we can layer on an explanation using valence bond theory. And what valence bond theory is going to do is basically explain that 3D shape. And so for something like okay, so so let's think about something simple like water. So I have this oxygen atom bonded to 2 hydrogens, and I have 2 lone pairs. It's bent, it has about 105-degree bond angle. And if we want to explain it, we really need to look at valence bond theory to explain how the electrons are really arranged so they can form these bonds. And so what we're going to do is we're going to take a look at our central atom. And we're going to look at the electron groups. And in this one, we have 4 electron groups. We have 2 bonds and 2 lone pairs. And if we were looking at Vesper theory, we would say these 4 things repel each other because they all have electrons, which are the same sign of charge, so they repel. So they'll arrange themselves as far apart from each other as possible. Now we're going to try to say what's really going on with the electrons there that allow that to happen. And what we're going to need to do is we're going to need to hybridize our orbitals to explain the arrangement of things around it. Otherwise, we'll have a 90-degree angle. And so that what I do in this case is I take that number of electron groups right there, or here, right here, and I say I need 4 orbitals to hybridize. To hold these 4 electron groups. Okay, so which orbitals do you take? Well, so I'm just going to kind of think about a energy diagram. I have my oxygen atom is in my second period. So if I'm thinking about just my valence electrons, I have those 2s electrons, right? And then I've got some 2p electrons. Great, 6. So I have 6 valence electrons, and they're going to be in the 2s and the 2p. And I don't really have any d orbitals that are available to me because I'm not in that n=3 energy levels. So there's no d orbitals. If there were, if I was looking at something in that 3rd row or below, I would also then have for like sulfur right under oxygen, I would have a set of empty d orbitals that I could also incorporate into my hybridization. But I just need 4, so I'm going to grab 4. I'm going to grab them from the bottom up. So I'm going to grab lowest energy first. So that's that 2s orbital, and then that's 1. And then I'm going to need 4 more orbitals. So I'll take one of those p's. I'll take another p, and I'll take another p, and I've got 4, so I can stop. I don't need to like go hunting for d orbitals. which don't exist in this energy level. So good. All right, so with that, I'm going to hybridize these into 4 hybridized orbitals. And their energy will be basically in between where the S and the P are. And so these are going to be sp3 hybridized orbitals. And they're all degenerate. They're all going to be at the same energy level. And we'll that's like a foreshadowing to Chem 163 way down the road when we start looking at what happens when they're not. Okay, so we're going to add in those 6 valence electrons again. 1, 2, 3, 4, 5, 6. All right, it looks really similar to what we had before, except remember the s orbital is just this circle, and these are each these p orbitals like this. So this will allow us to arrange 4 orbitals that all look the same with like a little nubbin like this around the oxygen, so they're all equally far apart, and they have that 105 to 109 degree bond angle. All right, so then I can kind of think about this oxygen. I can kind of layer this on top here as having these 4 hybridized, so one's going in and one's going to come out, orbitals right here. So these sp3 hybridized orbitals are these ones in black. And now I can put those electrons in them. So I can see that I have 2 of these are going to have 2 electrons in them. These are going to be my lone pairs. And then I have 2 that are going to be with 1 electron. These are going to be able to form covalent bonds, which they're going to do with these hydrogen atoms. And these hydrogen atoms just have an s orbital, right? So like the hydrogen just is 1s1. So there's not any hybridization we can do. It's just an s orbital. And so we can kind of think of it as overlapping right here, and it brings its own electron that it pairs with one of the oxygen atoms, and they overlap directly. And so this is kind of this valence bond picture. Now I can go in a little bit deeper and start looking at what types of bonds are forming. So in this case right here, we have 2 overlapping orbitals that are coming kind of head on with each other. This is going to be a sigma bond, which we call this. So in this case, I have 2 sigma bonds. And my oxygen is sp3 hybridized. And so that's what we're looking for when we kind of do an analysis of covalent bonding with valence bond theory. And it's going to explain how we really deal with these, or how we get these geometries. And then if we have a double bond, and I'm going to skip a lot of what we just did here just to kind of talk about something with a double bond. So let's just look at O2. Right, so we've got oxygen like this. So in this case, I can see that I have 3 electron groups, right? I have 2 lone pairs, and I have 1 bonded atom. So that means that with that 3, I need 3 orbitals to hybridize. Which I'll take my S first, and then my 2 of my P's, so it'll be SP, sorry, SP2 hybridized. And that's going to leave 1 p orbital. So if I want to show this using my orbital diagram. So here's just an oxygen, right? So I'm going to hybridize 3 of these. So these are my sp3 hybridized. And I still have 1 p orbital left over. So when I add in these electrons, I'm going to have 1, 2, 3, 4, 5, 6. I can see right here are my lone pairs. Here's 1 electron that's going to form a bond with the other oxygen. And then this extra electron in the p orbital is going to be used to create the double bond. like when we draw this, I'll do my sp3, or in green, I'll have my sp3 all 120 degrees apart. And 2 of these have lone pairs and 1 has just 1 electron. And then my other oxygen is going to look exactly the same. And then I have this leftover p orbital. Remember, these look like figure 8s. You can shade them in if you want. And these each have 1 electron in the p orbital. And so these are actually going to overlap and create like a hot dog around my oxygen. So these are going to overlap right here. And that's going to be my pi bond that forms. And I'll have 1 sigma bond because I have the overlapping sigma, and the pi ones are going to look like kind of like 2 things that are going to have it's going to have a node in the middle. And that's the big difference. All right, so that's kind of like my overview and example of valence bond theory. And you'll look at more complicated ones, and it'll explain our geometries like octahedral and trigonal bipyramidal and all of that. And it's super interesting. And it's kind of this nice little algorithm that if you follow all the little steps, you get this really pretty little picture that, you know, if you're into those sorts of things, is very satisfying to generate. So let's do a brief overview of MO theory. So again, MO theory, for problem solving strategies on this, we're just going to kind of focus on one piece in our introduction of it. And in higher level chemistry classes, you'll go into this in a lot more detail. So first we'll say that like this is really coming out of that quantum model of the atom and how electrons behave. And what we're going to do here is our molecular orbital is really like the wave function for the bond, like for the molecule. So we're going to see constructive and destructive interference. And so we'll have bonding orbitals that are constructive interference of overlapping waves. And we'll have anti-bonding orbitals that are really the deconstructive interference of 2 overlapping wave functions. So like if I'm going to bring together 2 s orbitals, right, to form a covalent bond, my bonding orbital will just look like one big happy blob of overlapping larger constructive interference waves, whereas my anti-bonding, these are going to repel each other essentially, have opposite signs, and they're going to have a node basically in between them. And so this would be a sigma bond when we would bring 2 s orbitals together, right? And so we would call this a sigma bonding orbital, and this would be a sigma anti-bonding orbital, which we like designate with just a little asterisk above it. You can also have pi bonding and pi anti-bonding. And then what we're going to do with these for our problem solving is we're going to build MO diagrams, and we're going to calculate bond order. And our lectures will introduce like the idea of resonance through valence bond theory and MO theory. And MO theory is great because it actually predicts resonance structures, like the hybrid structure that we would see in like when we actually characterize a molecule's bond lengths. And so that's kind of the power of MO theory. It actually gets us to something where we can predict things like bond lengths and also the magnetic properties of things, which none of our other theories are able to do. Like they can get to geometry, but they can't really explain how many unpaired electrons we actually have or see when we look at magnetic susceptibility data for molecules. But we're going to focus on MOs and diagrams and bond orders. And so I'll just give like a brief overview of these. Your MO diagram strategy is you're going to think about this on an energy level, and like you're bringing two atoms together. So like we're bringing our oxygen. Let's just do a simple one. We're going to bring like a hydrogen together, and let's actually do, sorry, I keep changing my mind. Fluorine together and fluorine together, right? I think this is an example we do in the lectures. And so you're always going to be looking at the valence electrons again, and not the core electrons, just because they're all going to pair up, and it's just going to kind of be a waste of time. So we have 2s and we have 2p for each fluorine atom if we're going to make F2. Right? And so they're each going to have 7 valence electrons in them. And we're going to look at how these wave functions for these electrons and orbitals around one atom are going to interfere with one another when they overlap, like when they share the same space. And so when they're going to essentially either add and increase the amplitude, or kind of subtract each other and decrease the amplitude, just like we were talking about in chapter 6 with just like string, or like how a string wave behaves. And so when we combine these, kind of the simplest version is for each orbitals that we bring together, we're going to create both a bonding and an anti-bonding orbital, and the anti-bonding orbital will be higher in energy. So if I'm bringing 2 s's together, this is going to look like either my bonding or my anti-bonding, like this. So my bonding one will be lower in energy, my anti-bonding will be higher in energy. Then I'm going to look at my P's. So when these combine, you're really thinking about like, how do I overlap two things like this so they can come together in the Z orientation? They can come together like this in the Y orientation, and if it's in the X, they're going to come together head on like this. And so we're going to have one example that's a sigma, where these are going to overlap and create, so for like the bonding, it would look like this. But these other ones right here are going to have a planar node through them, and so these are going to be pi. And so when we combine our 3 p orbitals and overlap them, we create 1 sigma and 2 pi, and we'll create the bonding and the anti-bonding version of that. And now the order of these, whether sigma or the pi are higher or lower in energy, will depend on the atoms that are combining. And so we'll talk through that rule set in the lectures. And then you just like go through and you fill in your total electrons. So I've got 14 total valence electrons from 2 fluorine. They each have 7. So I'll just go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. And I'm following the same rules I did for orbital diagrams. I'm going to fill from the bottom up. I'm going to half fill everything before I double up electrons. And then I'll be able to get a lot of information about bond order, and I'll get information about magnetic susceptibility of like if something's diamagnetic and everything's paired up, or paramagnetic and 1 electron is unpaired. The bond order is going to be equal to the number of bonding minus anti-bonding divided by 2. So in this case, we're going to get a bond order of, let's see, we've got 1, 2, 3, 4, 5, 6, 7, 8 bonding electrons minus 1, 2, 3, 4, 5, 6 minus 6 anti-bonding. And so those anti-bonding ones are right here. They're the ones that are high up. So this is like pi star, pi and sigma. And then those bonding ones are the ones that are in bonding orbitals that are lower in energy, right there. So it's going to be 2 divided by 2. It's going to have a bond order of 1. So that's going to signify that I have a single bond, which is what I would expect for two fluorine atoms forming a bond together. I would expect from the Lewis structure that it'd be a single bond. Right, that's MO theory and bond order, kind of in a nutshell. And again, more detail is in our lectures. Hopefully this overview is helpful, and good luck.